Hi everybody, I'm Nishchal Vivedi. I have just finished my PhD from Bhabha Atomic Research Center, Mumbai, and today I wish to talk about some experiments in quantum mechanics, which are very fundamental, and they have helped me throughout my research career to understand quantum phenomena better. So I wish to share this with you. Let me just put my presentation up. So this is my email ID. Anyone has any doubts can feel free to send me an email. Uh, when we learn quantum mechanics, we essentially have a lot of questions because quantum mechanics is inherently are not intuitive in nature. Um, we have questions like, what do matter waves really look like? Uh, why why do we really say that electrons can be either particles or waves? You know, we have statements like the particle interferes with itself. What does that really mean? And in general, what is this wave particle duality? This wave particle duality is sometimes also referred as complementarity, and uh, complementarity has a very close philosophical relation with the uncertainty principle. So there's this question that, does uncertainty govern complementarity? And I'm going to talk about an experiment about that as well. So these are the questions I'll try to answer. Let us begin with matter waves. So we all know what matter waves are. We have studied that in 1924, Louis de Broglie introduced the notion of matter waves. He gave a de Broglie wavelength, which essentially gave us a notion of waves existing, in matter, and that carried forward a lot of research in quantum mechanics. But this entire notion of matter waves was dramatized in 1989 by the group of Tonomura, um, which did a research in Hitachi Advanced Lab in Tokyo. And this was one of the first double-slit experiments with electrons. And the setup was that they tried to simulate they tried to simulate an double-slit geometry by using an electron biprism. The idea was similar to that of an optical biprism, but what they did was they essentially made a charged wire, which created a field around it, which deflected electrons on either sides of the positively charged wire. So after the electrons passing through these lenses, so-called electrostatic lenses, what essentially uh, happened was that they fell on something called as uh, a screen. Now, these screens were extremely state of the art, that when a single 50 keV electron stuck at a single place of the screen, it produced something like 500 photons, and it was an XY screen. It was a position sensitive screen. So wherever the electron fell, it produced something like 500 photons. And to add to that, they had a screen in front of them. They had a real-time monitor in which whenever the electron used to fall at a given place, the screen used to light up at that specific place. So this is how the setup looked like. The electrons came, and because of the positively charged wire and the electrostatic lenses created because of it, the electrons chose a path from either of the side, and they fall on the screen. Now there's something which we have to understand here. Electron is coming as a particle. The screen is a detector, and the screen is a detector which detects electron as a particle. Okay, so the electron comes as a particle or as a quantum particle. What I mean by it, electron comes and it just sees the positive force field or the electrostatic lens, and it takes a decision of going on either way depending on from where it is falling, and it goes and hits at a given point in the screen. Now this entire setup was such that uh, there could only be one electron, that they were able to tune it in such a way that there was always one electron in the system. They could do it at the rate of one electron at a time. So let us first look at the results. If you just have a single slit coming through, there are no two slits. There's just will, or it's as good as we block one of the slits, and from the other slit we are getting the electron beam. So this is the result. 10 electrons, you see some dots here and there, some places which have been brightened up. 100 electrons, you see more such bright spots, being spread uniformly. 3000 electrons, somewhat random and uniform distribution we see. By the time we reach to 20,000 electrons, we see, if we stare at the figure a bit more, we actually see that, yeah, maybe the electrons are gathering here a bit more. So around 70,000 events, we actually essentially see uh, a, a maxima somewhere here. A lot of electrons have gathered here and decided to fall here as compared to the other places. So a lot of electrons have actually fallen here. And this corresponds to the classical result of a particle. It's a single slit experiment. Now the question is, let's jump into the experiment which we have come here to do, the double slit experiment. So when we do the double slit experiment, 10 electrons, after 10 events, 1 electron coming at a time, we see that the electrons are here, they choose some or the other positions and they just sit here. Very simple, very, nothing can be drawn conclusive from there. After 100 events, we essentially see that there is a distribution of electrons, but so far very uniform and very random. 3000 events, also we see that it looks like a fairly random, fairly uniform distribution. Something around 20,000 events, also it looks pretty, pretty randomly distributed. But if you stare for this picture for a very long time, you may be able to see that there are a certain kind of a fringe pattern. There are certain positions where electrons have chosen to fall more as compared to the other places. When we do 70,000 events, we can clearly see fringe patterns. Now, what are these fringe patterns? This is an experimental result. We have electrons coming one at a time and settling down on the screen. And this is essentially, finally, eventually, after a lot of events, has actually shown us some kind of fringe pattern where electrons are actually choosing to be more at some places, and they are not preferring other places on the screen as much as these places. Why is this happening? What does this really mean? Turns out, if we do interference, if we do calculations which correspond to interference of light, say for example, and if we do similar calculations, we essentially see that the factors like the bandwidth, etc., which if we find out, they match, the results match very nicely with that of interference experiments, if we treat these to be two waves interfering. But the question is, what is interfering with what? Because if you remember, there was just one electron in the system at a time, right? There was no second entity with which the electron could have interfered. Because of which, the first logical conclusion which was drawn out by this was that, well, maybe the electron interferes with itself. Because when we have a single slit, we do not see this pattern. We just see a normal classical result. But we get a wave-like interference pattern is something which we get once we are into a double slit experiment. So this could clearly mean that there has been an interference, because there is an evidence of interference, and this interference could have only occurred if the electron which is there in the system would have interfered with something. But that something is nothing but but because there was nothing else in the system except that electron, that could mean that the electron has interfered with itself. But does this make sense? Is a question. But this was one of the very popular explanations for this thing. Turns out that this explanation, which we see that interference occurs when both the slits are open, is governed by something very subtle. It is governed by the notion that we closing one of the slits does not affect the motion of or the physics of the electrons at some other point. This is called as the principle of locality. So if we abandon this principle of locality, we no longer need to assume that the electrons interfered with themselves. The principle of locality has been the very guiding principle in classical physics, that how can an event occurring at a place A affect the physics of events are occurring at a place B. So non-locality appears to be an inherent an inherent property of quantum phenomena, and because of this non-locality, a lot of unintuitive results occur in the quantum universe. And this is not just with electrons. If you look at neutrons, we get a similar fringe pattern, which can be explained by double slit kind of derivation, like wave interference kind of derivation. If we so this was an experiment by Anton Zeilinger. Um, uh, M.R. Andrews and his co-workers essentially produced two Bose-Einstein condensates in two separate wells, and then they opened the well in such a way that these two BECs were contained and they were interfering together. And this interference essentially led to such kind of patterns, which you can clearly see that there is an interference pattern observed even in Bose-Einstein condensates. So this is exciting. All quantum particles appear to agree to this. So non-locality is something interesting, and non-locality is something which quantum mechanics and quantum particles are known to exhibit. And this is the inherent thing which we say that we cannot imagine quantum mechanics, because we essentially are unable to, being classical particles, we essentially are unable to imagine non-locality. This is one of the things. The other thing which we had observed here in the next question, which essentially comes, is that of complementarity. Electrons and particles exhibit, depending on what experiment you are doing, these quantum particles exhibit wave nature or particle nature. So classical physics, this is very different from classical physics because it has a unity in the description of objects. And this duality is something which comes up only in the quantum regime. Mr. Niels Bohr, Dr. Niels Bohr, the great guy, was able to recognize this as the presence of duality in the quantum regime. And the quantum objects exhibit this dual nature of either being a wave or a particle. This definition was further extended as complementarity being something which quantum mechanics allows us to know. As you know, that Heisenberg gave his uncertainty principle, and the uncertainty principle essentially, like if we consider the position and the momentum uncertainty, as we know that if you measure position quite accurately, you will lose the accuracy in momentum, and vice versa. So here also the uncertainty principle also somehow hinted to the complementarity definition, that it was either the position or the momentum which the quantum mechanics was somehow allowing you to measure. So there was this inherent question, which actually was asked by a lot of people, that does uncertainty principle govern the complementarity? So this was a question, that is it the uncertainty principle which is causing complementarity? Is complementarity a result of uncertainty, or some other corollary, something like that? There were a lot of theories about it until there was an experiment. So the experiment, to be designed experiment for such a situation, would be something which does not maybe violate an uncertainty principle, and we are essentially just able to observe the wave particle duality without violating the uncertainty principle. If uncertainty principle and complementarity are not related to each other, then despite of n- you know, and if we are keeping the uncertainty principle intact, even then we'll see a change from wave to particle nature. But if they are related to each other, if uncertainty governs complementarity, then if we do not violate the uncertainty principle, then we should be able to see the same wave nature of the quantum system. That was the fundamental philosophy of the experiment. This experiment was finally performed in 1998 by Rempe and his co-workers. They designed an apparatus which looked something like this. So the beam A came and it was split into B and C. Now, this beam was of rubidium atoms. Rubidium atoms were allowed to fall, and they were constructed in such a way. These reflections, these beam splitters, essentially were designed in such a way that after there was a split from B and C to D and F and E and G, the essential initial momentum of the particles were known. So the delta P was essentially known. So delta P was known and it was around 0. So with this, the maximum uncertainty goes in the delta X part. So the experiment was designed in such a way that the delta X is not restricted and the position measurements are totally not done, are not done essentially. But this is how the experiment was designed, which essentially led to them not violating the uncertainty principle. So here B gets divided into D and F, and C gets divided into H and G. D and E were allowed to interfere, and F and G were allowed to interfere. And as we can see, these atoms exhibit fringe patterns and they exhibit the wave nature. You can see here as well, we can see the wave nature of the, we can see something like an interference pattern over here of rubidium atoms. What did they did do next is, here at the second beam splitter, what they essentially did is um, they threw a microwave here. So what microwave essentially did to these rubidium atoms was that it divided them into two parts, one with 2 h cross angular momentum and other with 3 h cross angular momentum. And same with C, 2 h cross and 3 h cross angular momentum. So essentially rubidium atoms had these two angular momentums, 2 h cross and 3 h cross, the way they were prepared. The microwave did essentially just separated both of these angular momentums. And the 2 h crosses were allowed to interfere and the 3 h crosses were allowed to interfere. Now here, they made sure that the atoms are not localized, because localization is one of the most important part of uncertainty principle. Even when we are talking about the double slit experiment, the atoms are localized in the region of the size equal to the separation between the slits. So therefore, the uncertainty principle was not violated, and the rubidium atoms were free particles and they were moving freely. Hence, the uncertainty principle was not violated, and the localization of the experiment itself. Of course, you are having an experiment in a setup, and since the experiment is there in a setup, that essentially has some kind of localization in it. But it was made sure that this localization is extremely huge, so huge that does not affect the quantum scales. So the observables were something like 4 magnitudes greater. And they did this thing with the with the rubidium atoms, and turned out there was a loss of the wave nature. Now, since the Heisenberg uncertainty principle was not violated, if complementarity was governed by Heisenberg uncertainty principle, even after applying these microwaves, since they were still the quantum particles, and it was still, they were still allowed to interfere, the wave nature should have remained intact. That was the argument. And by this argument, it was essentially shown that complementarity and uncertainty are two different and two unrelated concepts. So while studying quantum mechanics, we come across these concepts, and these concepts have personally bothered me very much in actually trying to put your finger that what essentially is this duality, how does this duality look like, are they just hypotheses, or they are essentially very cleverly and crafted experiments which have actually led us to this result. So turns out that there are all these experiments, beautiful experiments, which were conducted in the last century, and these experiments have essentially developed our intuition of quantum mechanics. Though we cannot imagine and we cannot have a intuition in quantum mechanics, the only way to develop intuition of quantum mechanics is to understand how these experiments are and how these experiments are designed, and it's very crucial in understanding a lot of statements which, if not used correctly, can lead you into trouble. So this is all about my talk. We discussed complementarity and matter waves and uncertainty principle. There's my email ID in case people have any questions. Please feel free to contact me. Stay indoors, stay safe, uh, enjoy, and study a lot during this quarantine. Thank you very much.